Good afternoon, and thanks to Stuart and the organizers for having me here. I want to present from work from the Google Artificial Intelligence Lab and tell you a little bit about our experiences in building actual quantum processors, and then maybe relaying some insights, some learnings from this effort to this community who is interested in whether quantum effects do play a role in higher brain function. And I will go from sort of more hard engineering to more speculative ideas. So first I want to explain you an experiment that you may have read in the news about, and knock on wood, we hope to be able to perform it later this year. And this is the so-called quantum supremacy experiment. It's a bit unfortunate name, but it was given by the Feynman professor at Caltech, John Preskill, and then it was refined, for example, by Sergio on our team. But the basic idea of quantum supremacy is that you have a well-defined computational task, and you have a quantum processor that can do this task in a short time, say a second, while even the fastest classical supercomputers that would be currently Taiwan Light in China would not be able to do this in a reasonable time, let's say a year. Note, however, that for this benchmarking, it's not necessarily required that it's a useful task. It can be an exotic mathematical problem. So how do we perform this experiment? Of course, if you want to win with a quantum processor, it's maybe best to start on the home turf of the quantum processor, and you write down a quantum algorithm. And you may not be familiar with this notation here. The details don't matter so much. I often refer to it as quantum sheet music. It has three basic parts. You start your qubits in time 0. Let's say here I all started them in the 0 state. And then there's a bunch of gates that either act on a single qubit or on 2 qubits. And you apply a number of those gates, and then at the end of the day you will have a quantum state, and possibly it can be a superposition state that is sort of a very broad entangled superposition over, if you had n qubits to start with, could have support over 2 to the n classical bit strings. So the Hilbert space involved here is 2 to the number of qubits you start with. And then you will, at the end, measure the state. But measuring a quantum state is really sampling from a probability distribution encoded in this quantum state. So the next thing you're going to do is you take your quantum chip, and here you see actually our latest chip. It's a 22-qubit chip and sits in our labs in Santa Barbara. We use superconducting qubits, and they operate in these devices that you see here to the left, so-called dilution refrigerators. They keep the chips at about 10 millikelvin. And so the little quantum algorithms that I showed you can be put onto the quantum chips. That's what they're made for. And then I can do this protocol and essentially measure m bit strings. So I take m samples from this probability distribution. And then next thing is I will try to see with which probabilities should I have seen those samples. And we initially worked together with high-performance computing experts at Intel. It's nicer to play against a red team, not play against yourself. And they managed to push this to 42 qubits. So for 42 qubits, they used the Edison computer from Department of Energy. And with that, they were able to give us the exact probabilities with which you should have seen the bit strings when you measure. But just a few weeks ago, there was a team, collaborators of ours, Damien Steiger and Thomas Hanner from ETH Zurich, who improved this. They pushed it to 45 qubits, booking out this machine here on the picture. This is Corey 2 at the US Lawrence Berkeley National Laboratory. It's one of the top supercomputers in the world, and you had to clean this thing out for a whole day to compute the probabilities that the circuits that I showed you produces. And then you're kind of done. And the task is to show that the samples from this probability distribution that your processor, your quantum processor, produces are close enough to the ideal distributions that you wrote down on paper by defining your quantum algorithm, that no classical machine could produce samples of similar quality. And this chart here is a little bit to illustrate why is this a hard task in the first place. It is a hard task in the first place because it's, I don't know whether you have ever seen this, and sometimes I bring a demo along like a little laser, where if you've seen those laser speckles, these intricate patterns that laser produces. This is probably too weak to do this. And those speckle patterns, they come about because it's a coherent light source. So when it goes through a diffuser, let's say some glass, then you have a lot of different pathways the light can go. And sometimes you have constructive, sometimes you have destructive interference, and that makes these very intricate patterns. Versus an incoherent light source, if you would just have taken an LED and shine against the wall, then you get sort of this washed out pattern. So basically, because we have a very coherent device, you get these speckle patterns, but now in Hilbert space, in qubit space. And therefore, the probability distribution that you will measure from or draw samples from has this very intricate speckle-like shape. And essentially what's shown here is if I have n qubits, I can get as measurements bit strings of length n. So I measure n zeros or 1. And here in this picture, they are sorted. So the probabilities from the bit string 000 all the way to the bit string 1111. And it's like the bits of a very, very fine key. And you need to sort of draw samples according to this very complicated function. Actually, it turns out, however, that if you were to reorder those probabilities from the smallest to the largest, you see actually there is structure in this probability distribution, and you get this exponential shape, and it's a so-called Porter-Thomas distribution. And it's essentially the distribution you get if you pick randomly in your n-dimensional Hilbert space a state and then ask what are the probabilities to see the different components of this large superposition state that will be distributed according to this probability distribution. And therefore, if you try to be sort of a classical imposter, you say, oh, I can do this with some classical black box, I don't need a quantum computer, then the challenge is, let's say, take a very simple-minded imposter, just the uniform distribution. If you would just uniformly draw some strings here, chances are you will pick them somewhere here from the middle, but you will miss the ones with the high probabilities. But a good sampler should sample more from the high probability point. And therefore, it's a hard task. And actually, complexity theorists will tell you that if you have a classical machine that tries to produce such samples, the cost is exponential in the number of qubits. And therefore, if you push it to about 49 qubits, then even the largest machine will fall over, because you have to maintain 2 to the 49 complex numbers somewhere on the scratch pad. And that is, we still have machines with enough RAM to keep that many complex numbers. But in every step of your computation, these numbers have to talk to each other. And that creates a huge communication bandwidth need that no computer has and will not have. And versus, I skip the rest of the slides. This is essentially to say you can introduce a measure called the cross entropy, which is a figure of merit that says, yes, these samples really come from a certain probability distribution or not. And then you see that the hardware will be able to produce samples of high cross entropy difference, sort of high quality versus no classical machine can give you high quality samples in reasonable time. Okay, so this is quantum supremacy experiment, and to go forward, I wanted to explain you one important notion that when you hear about quantum computers, you should know. And this is the space-time volume of a quantum computation. Essentially, how our bits are organized, we have two-dimensional chips, so they sit there as a little array, think of like a little sort of square lattice, let's say 7 by 7 qubits. And actually a good way to think of qubits, this was mentioned a few times in previous talks, is to think of them or of their state as vectors on a sphere, the so-called Bloch sphere. And then you come in with your gates to manipulate your qubits. And a gate, you can think of it, will rotate those vectors around. And a single qubit gate will just look at one single qubit, rotate it around a certain axis. And the two qubit gates might do this conditioned on the state of another qubit. So you look the qubit to the left and what state it is, and then according to the state, you turn the other qubit by a certain angle, and then at the end of the day, you measure. So in the beginning, we won't have enough qubits to do error correction. And therefore, we can only have space-time volumes, meaning so the two space axes are again 7 by 7, and then the time axis is how many gates I apply to each qubit. And we have very high fidelity gates, so we approach a 3/9 fidelity. It's actually required to do a successful supremacy experiment, but there's still a bit of error. And unless you correct it, you have to think of your quantum processor as you have a certain budget of gates you can execute. And then every time you execute a gate, it gets a little bit noisier and noisier, so you have to end at a certain time. And so therefore you have a finite space-time volume. But if you look how quantum computing will develop, the fidelity will get higher, and therefore the space-time volumes will get larger. And eventually we have enough qubits to do quantum error correction, and then you can go on the time axis as long as your patience for the result allows you. So therefore, we think that this year we should be able to do the quantum supremacy experiment. Far out there, once we have error-corrected quantum computers, there is a whole candy store of algorithms such as unstructured search, factoring, semi-definite programming that you can run and where there are proven speedups. But the big question is in between. Are there, for processors that have passed the supremacy frontier but are not error corrected yet, can we do useful things with those? And after the Monday talk, many people came up and asked me, so what is the first useful application rather than an exotic benchmark? And it will be what Feynman already identified early on. Feynman's killer application is actually a simulation of other quantum systems. And you might think, oh, this sounds very inbred, but it's actually very important. If you want to make a better battery, better solar cells, better catalysts for a pharmaceutical industry, on and on and on. Whenever you do sort of engineering on a nano level where quantum effects play a role, then today you have no good tool to simulate such systems, but those processes will allow you to do that. And actually just last week, we published a nice breakthrough in this direction that actually we have quantum simulation algorithms now that are likely to fit into these early space-time volumes that we can support pre-error correction. Okay, so here's the first maybe message to this community, and that is the following. Like Stuart often points out that a paramecium, a single-cell organism, can do all these amazing things, such as finding a mate, avoiding an obstacle, even do simple learning tasks. And as a roboticist, you have some respect for this. These things are not that easy to program. So what I just told you is that a rather small quantum circuit with just 49 qubits and just 30 to 40 circuit depths, so 30 to 40 gates per qubit, that's already supercomputer level stuff. And there's just plenty of opportunity to tuck such a little circuit away somewhere in living organisms. I'm not saying that the coherence environment is necessarily all there, but the message is there are just many places where you can tuck away a supercomputer grade machinery inside some living system. Okay, so let's play around with these early quantum circuits and see what we can do. And a recent game that I'm playing with my co-workers Edward Farhi, Jeffrey Goldstone, and Samuel Gutmann is to do quantum neural networks on these near-term processors. And I've seen earlier some slides for neural networks. These circuits here don't look too different. Again, you can present an input pattern by setting your qubits up, down, so you present a binary input pattern, you push it through your gates, and then you go to one qubit and you measure the qubit, let's say in the y direction, and if your qubit points in the plus y direction, then you declare the label to be +1, otherwise it's a -1. So it's a straightforward way to represent a Boolean function, and you can, very similar how you would do it with neural networks, you can define a loss function, which essentially counts how many times are you doing correct or incorrect classification on your training example. And then I told you earlier that you can think of these gates as sort of they rotate the qubits. So instead of weights like in neurons, you have angles in these gates. And essentially by changing these angles, you change the input-output function. And you can now ask questions that a machine learning person would ask. Can I classify something with lower time complexity than a classical network? Do I need less samples? You know, that machine learning people always want to know how many training samples do I need to train a certain architecture to drop below a certain training error. Yeah, I can also ask how bad is it if my data is polluted. And there are actually a number of new games to play when you consider quantum neural networks. And for example, the answer, can I get away with a shorter quantum neural network than what I would get away with classically? And the answer is probably yes, and I realize this is a bit of an arm wavy answer, but you could have sort of, let's say, formalizing factoring as a decision problem. So it's a Boolean function that you may want to choose to learn, and we know that a quantum circuit can do this in polynomial lengths, while the classical neural network or the classical circuit would have to be exponentially long. So there will be such advantages. You can also do things that have no classical analog. I can present multiple examples at the same time in quantum superposition. So what does that do? And finally, the outer loop of this algorithm, which means to set your angles in your gates, the 3 parameters you have for each gate, you could use quantum enhanced optimization to achieve this learning task. And let me tell you a little bit about this letter. And in previous presentations here at the Science of Consciousness conference, I've told about quantum enhanced, or spoken about quantum enhanced optimization and quantum annealing. And I just wanted to give you a late-breaking update where we have been in this. So learning means you have sort of this objective function, and your task is to find a low point. Low point means low training error. A high point means you make a lot of errors. So your task is to find the gate setting, the angle settings that produce a low point. So the way how we formulate this today, and this is a little bit evolved from where we used to be, we use sort of a classical dissipative dynamic. So one that can exchange energy with the environment. Dissipative means if I go down this energy landscape, I have to get rid of energy. I have to give this back to the environment. And that is what a classical, let's say, for example, I could use steepest descent, a gradient descent, and then I come down. But then eventually I will be stuck in a local minimum, and quantum processes can help you with escape from a local minimum. And in the past, we have sort of demonstrated that if your energy landscape has very tall and narrow barriers, quantum tunneling will get through these barriers with higher probability than sort of a thermal classical over the barrier escape. So you have two ways to improve on your optimization or escaping a local minimum as compared to classical. But we recently found there's actually much more intricate physics going on, basin of attraction to a different valley, and from there you can hopefully find a lower, better energy point. And it's essentially the physics that you use to understand conduction in a metal. So if you ask, how do electrons make it through a metal? It's a similar physics that is being used here. And it turns out that you can get through this energy landscape at least quadratically faster than what is possible classical. And there's actually a simple case that they considered. It's a so-called impurity band. And this is just the most extreme case. You have sort of two local minima, and all the other energy states are sort of high up there. So it's like the landscape is like a flat table. There are two holes in it, and you start out in one valley, and you need to find the other one. And then if you analyze this, you find the following. You find that the time so there's this rather complex formula that shows how quantum mechanically these two states are coupled. And never mind the whole formula, just look at the exponent here. There's a 2 to the minus n half. And that's rather exciting. You might not immediately find that so exciting, but it's exciting because it's quadratically faster than what's classically possible. Classically, it's an unstructured search problem. If sort of your optimization landscape is flat, there are only two local minima, you start in one, I give you no guidance where the other one is, then it will take you essentially linear time. It will take you 2 to the n for any class. For the best, it's easy to prove, the best classical algorithm will take time steps 2 to the n, while here, using this many-body delocalization physics, you get there quadratically faster and only in 2 to the minus n half steps. And this other point can actually be rather far away. So that's why we are getting more and more convinced that quantum-enhanced optimization in general will do better than what you're classically able to do. Okay, so from here, two more lessons. One is that shallow quantum circuits can act as learners. To be honest, the exact properties are not yet known. This is sort of a new area of study. But we have good reason to hope that there are advantages in time complexity, in robustness to label noise, and sample complexity. And another observation, this is more sort of targeted to my colleagues, the ones that were earlier mentioned by Joska, that do traditional machine learning. They will say, come on, Hartmut, how many qubits do you have? Like 50. And you go circuit depths of 50, that's just tiny. We use neural networks that have literally 1 billion parameters to tweak, and there are millions of input parameters. So what can you do with your little quantum neural net? But of course, what we can always do is we can just replace the last layers in a deep neural net by a quantum neural net. And if there are advantages to a quantum neural network, we can have such a hybrid architecture. That's why I like to show you sort of the quantum neural network sitting in a single cell. I could actually think of the quantum layers are just sort of the executive decision-making level for a much larger neural network, which in part may be classical. So that's a possible scenario. Okay, so I come to the last part of my talk, and the nice thing about this conference is it sort of encourages you to go to places where you cannot say sort of just hard, crisp things like we typically strive for in engineering. And that's about subjective experience in machine learning. And So not too long ago, I went through an episode that reminded me of the stark difference between human learning and machine learning. Actually, I have a little boy, and I tried to teach him how to ride a bike. So we went out in the street, I sort of helped him up, stay on his little bike, and it didn't go too well, and then me, bad dad, I said, hey, come on, you're a little clumsy. Shit, I shouldn't have said this. And I was devastated, like, really, Dad, I'm clumsy. Okay, so the next day we went out, like I held him on his bike, and somehow he got it, so he zoomed down the street, and he was just so happy, like every single fiber of his being, like, yeah, I got that. And I sort of, as a machine learning person, I was just, yeah, that's obvious. We all know this firsthand, that there's essentially a congruence between learning success and a pleasant feeling. And if you subscribe to materialist worldview, let's say something that Roger put forth, then you can get around from assuming that there must be certain states of matter or certain evolutions of states of matter that feel better than others. Yet, nor physics nor computer science has any model, barring sort of ones that we can't really implement. We don't really have a model of what constitutes a state of matter that feels pleasant. And I would even argue that, not knowing this, but I think we can make some arguments why I think a machine learner is unlikely to have this congruence between success in pattern classification and pleasant feeling. And the reason is as follows. Even though the overall situation, let's say if I were to program a robot to ride a bike, then the overall situation is not symmetric. There are right actions and wrong actions. As I know, in these times of fake news, we seem to forget that there is objective right and wrong often. You either fall over with your bike or you don't. So there is an asymmetry there. But then, if you look closer how machine learning people implement it, they look at their loss functions, they look, do I go down, or did I do this last pattern right or wrong, and then I have a plus or minus, I get a positive signal or a negative signal, or I get a larger loss or smaller loss. But at the end of the day, let's say, for example, setting the sign differently, it's just setting a 1 instead of a 0 somewhere. And it's just hard to argue that if, let's say, having the 1 over here, as opposed to shifting it over a few memory cells, that if that state, let's say, feels good, that suddenly this other state here feels bad, or vice versa. It's just too similar. And if you go even lower and look how the zeros and ones are implemented, let's say, like in a flip-flop circuit, it's just symmetrical again. And to be even more extreme, I could have just changed the labels of, let's say, the +1 and -1 in my learner and put a long cable to another little system that all it will do is change the sign again. Then this whole initial piece would operate, but just inversely. So the pleasant and unpleasant feelings should just switch. So I think it is implausible. And in a way, if you think about it, if you don't have a model for what constitutes a pleasant or unpleasant state, it would be miraculous if you would have implement our learning routine such that this coincides, or you have this congruence for a machine learner as well. I would rather think it would, if anything, it would feel confused. So I took time to doodle around a little bit. I thought, okay, can we, with our new quantum computer, could we have now quite some mastery to a high degree of fidelity to produce states of matter and to go through evolutions of state of matter? Could we possibly organize it such that we build an AI Skinner box? We make it go through a pleasant experience, and then we want the circuit to ask for more. But it didn't get very far. Let's say you start with a decision where with a certain probability you do something that's pleasant, and with a certain probability 1 minus p, you do something that's unpleasant. How would you proceed from here if you would assume that you have some measurement device that can tell you how happy you were when you went through this process? Then it's rather straightforward. You can go back and you update your p so that you go more to the happy branch. But in the absence of somebody who makes a suggestion how to measure this happy operator, then we can't really do it. I have no idea. But the last slides, I want to sort of offer up a proposal. Now, so again, we stay in the materialist worldview and say that pleasant states or pleasantness or unpleasantness must be associated with a state of matter or its evolution. And what I would like to explore is the notion that relaxing to a stable state is associated with a pleasant feeling, and evolving to an excited state is associated with anxiety. And it's maybe telling that physicists already use these psychological notions. There was no need for it, really, to call it such. And essentially what you would find is if you adopt this notion, there is this interesting idea or observation that physical and psychological perspectives become congruent. Yeah, so the physicist would say the system evolves this way because it minimizes Gibbs free energy, but a psychologist would say, no, it does this because it feels pleasant. And there's, of course, also logical consistency. An organism that has pleasure in doing things that destabilize it, this organism will not be around for very long. And there are also engineering advantages to mapping patterns or, let's say, positive learning results to stable states. We already saw that now you can take advantage of quantum tunneling. And also, if you use stable states in a deliberate way, you find that this helps you stabilizing percepts and behavior patterns in the presence of noisy sensor readings. Okay, and the very final thing, with this notion that relaxing to a stable state feels pleasant, you could think of psychedelics as literally a catalyst for the state of mind. Yeah? Because again, if you're a materialist, you must be in some state of mind, and what happens if this is catalyzed somehow and goes through a typical chemical reaction. So we think of psychedelics as nothing more than this, how to catalyze a reaction. And then we can ask the question, what would happen if you're in a state of mind, a catalyst comes in, and you go, let's say, through a tunneling transition. That's sort of an interesting thing to think through. And to me, it explains one piece. I sort of, for about 10 years, I'm working with an Amazonian entheogen called ayahuasca. And sort of every time, even though I do it for 10 years, it's sort of the same thing. The onset of the experience is very scary. You're anxiety-ridden, and once you come out on the other side, this feels extremely peaceful. And maybe it's just me, a scaredy cat, but looking at my fellow folks who go through these experiences as well, it seems to be similar to everyone. So this notion that destabilizing is associated with anxiety, stabilizing with pleasantness would sort of fit this here too. And then you also have this nice situation that you have sort of this double description. Finding this lower state here. In computer science, or computer scientists would say, you found a solution to a problem. But in physiological terms, you may say you relaxed, or this relaxation corresponded to finding a more stable homeostatic equilibrium. So kind of healing and problem solving sort of goes together here in this model. Okay, I think I outrun my time. So this is the team in Venice Beach and Santa Barbara, the software and hardware teams for the Quantum AI group. And thank you.